Hi everyone, we're set to go with section 8.2 in your calculus book. This time we're going to be looking at the area as defined as an integral in two-dimensional space. So let's get going with that and we'll see what I'm talking about. Over here we're told that the area of a region R between curves, one can compute the sum of non-overlapping rectangular areas to almost fill the region R. So basically you're just drawing a bunch of rectangles and they're kind of filling in there. Not exactly, but close to it. So that integral symbol followed by f of x evokes the notion of an infinite sum of rectangular areas having the dimensions of f of x and d of x. So f of x is going to be that horizontal dimension, and dx is going to be the, I have that backwards, don't I? F of x is going to be the vertical dimension, and dx is going to be the horizontal dimension. Now it's always important that you know which ones is which. If you're drawing your rectangles to be vertical or if you're drawing them to be horizontal. In the easy case, we're starting off with the vertical rectangles here. So for the example over here, we can fill R approximately with rectangles of height f of x minus g of x and width of dx. So that f of x minus g of x, that's going to be the height of the rectangle. There are a couple of formulas that we can start with right now. This first one says that the area is equal to the integral from the minimum x to the maximum x, the minimum x to the maximum x of the upper function minus the lower function. Now that's if you're going to draw your rectangles vertically. Of course, there is an analog if you draw your rectangles horizontally. That analog over here is the integral of the y minimum to the y maximum of the function on the right minus the function on the left. So we'll take a look at this. Number one, express the areas of the regions shown using definite integrals without absolute values. Where applicable, use a rectangular section shown to guide you to set up the correct integral expression. Okay, so we're going to have to look at the four boundaries here of interest. The rectangles here are vertical, so we're going to get a delta x or a dx in our integral. The minimum value is a, and you can see that minimum value right over here at x equals a. And then we're going to get a maximum value at x equals b. And you can see that right over here. The upper function is f of x right over here, tracing out. And then the lower function is y equals 0. So again, the upper function, y equals f of x. The lower function, y equals 0. And then when you put that all together, you get the integral from a to b of f of x minus 0 dx. For question 2, something interesting happens. We have vertical rectangles again. That's going to indicate a delta x. But now if you notice, the top function is going to change right here at x equals c. On the left of that, you have the top function is x equals 0. X equals 0 is this function right here. That's the top boundary. And then from c to b, the top function is going to be this right here, which is f of x. So because the top function changes over there at x equals c, we're going to need two integrals to evaluate this. Or you might want to think about this as there are going to be two different areas. So we'll need those two integrals. So let's just take a look at this area on the left. On that area on the left, the minimum x is a and the maximum x is c. The upper function, like we stated before, was y equals 0, and the lower function is going to be f of x. That's going to give us this integral, which would be the integral from a to c of 0 minus f of x, or just negative f of x if you prefer. Now the second area on the right over here, we're going to notice that the top function here, well, first of all, we're going to start from a minimum value of c to a maximum x value of b. The top function here is f of x, and the lower function here is 0. So now that we have the top, bottom, left, and right, we can put together an integral. And that integral is the integral from c to b of f of x minus 0, or if you prefer, just the integral from c to b of f of x. Put those both together, and by put them both together I mean add them, and you should get the area of the entire shaded region, which is just going to be the integral from a to c of negative f of x plus the integral from c to b of f of x. Okay, so we're on a roll now. Take a look at question 3. We've got vertical rectangles with a minimum x value of a and a maximum x value of b. We got an upper function of f of x and a lower function of g of x, meaning you get this integral, the integral from a to b of f of x minus g of x. Question 4, that one looks similar to question 2. Notice that the upper function again changes right here at x equals c. So again, you're going to need 2 integrals here to do this one, and I'll leave this one to you. Question 5, things kind of change on us. So the first thing I want you to notice is that if you try to integrate this as top function minus bottom function, right over here you're going to get a rectangle where the top function and the bottom function are the exact same function. So that's peculiar. That should never happen. It's fine if it switches, but if it's the same function, then something weird's going to happen. And the other thing that I want you to notice is that if we try the vertical line test, these aren't functions. Neither f of x nor g of x are not functions in terms of the classical f of x point of view of things. So we are going to have to do something different, and something different means that we're going to approach this as a delta y problem. So we're going to integrate this from the lower y equals a to the upper y equals b, and we'll take a look at that formula again, right over here. We're going to integrate from a lower y equals a to an upper y equals b, and we're going to do the right function minus the left function. Okay, I think it's pretty easy to see here the lowest value of y is c, and the upper value of y, the highest value of y, is going to be d. So we're going to be integrating from c to d. Now let's look at that region and see if we can find out which of these is the function on the right. And this is the function on the right. I'm tracing it out in red. And if we keep on going, we notice that that is actually g of x. So the function on the right is g of x. This means that if you trace out the function on the left, you get f of x. F of x is that function on the left. At least it's the function on the left for our region. So if we got that, lower is c, upper is d. The function on the right is g, and the function on the left is f. That gives us this integral. The integral from c to d, g minus f. Notice that everything is in terms of y. There's not an x coordinate anywhere. The functions are in terms of y, so when you write out your integral, you shouldn't see the letter x, you should only see the letter y. And if you're nervous about integrating in terms of y, you're always free just to change all the x's into y. That's not going to affect anything, since the variable of integration is in effect a dummy variable. It has no sense of what is what, or what its physically corresponding to, at least once you get down to the integral level. Okay, question 6 I'm going to leave to you as well, and that brings us to question 7. Let's take a look at that. All right, so we've got the graph of y squared equals 4x squared minus x to the 4th power. First thing here is let's check and see which rectangle works best. And if I tried vertical rectangles, which is pretty much default, vertical rectangles, that goes from that top function to the bottom function. And I know it looks like we only have one function here, but remember that you can write this as positive and negative square roots, which we're going to have to do eventually. And if you try to do left versus right, that just gets even muddier, I think. So I'm going to approach this as top minus bottom. The next thing I like to do when I teach is I like to say look at symmetry, because symmetry is going to help you as you integrate things, especially down the line when you have to start evaluating it. So this figure here does have x-axis symmetry and it has y-axis symmetry. But I think that y-axis symmetry is going to be more important to us because we've already decided that our rectangles are going to be vertical rectangles. So in other words, we only have to integrate from here to about here, wherever that is. And that does look like it's at x equals 2, but you're going to want to solve and make sure. Don't let the diagram lie to you. Okay, like I mentioned before, we have a positive root and a negative root if we solve for y, which means that that upper function here, this is my y1, the positive square root of 4x squared minus x to the 4th. And then down over here on the bottom side, that's going to be my negative square root of 4x squared minus x to the 4th. Now, we're going to have to figure out how tall, what's the vertical dimension of this rectangle. So it's going to be a difference in y coordinates. It's going to be y1 minus y2. The vertical height of these rectangles, which I like to call L, that's going to be y1 minus y2, which algebraically is 2 root 4x squared minus x to the 4th. Next, intersection points. Now that is pretty much 0, although we'll prove that algebraically as well. This looks like 2. We want to show that algebraically as well. Those intersection points happen when y1 equals y2, which basically means when the positive and negative roots are equal to each other. And so we're going to find out what coordinates, x coordinates, are those positive and negative roots equal to each other. So take the square root. I know it's really tempting to square both sides right now, but I think the smarter plan here is to move everything to the left side of the equality. So imagine adding the two roots together. That's going to give you that 2 of those roots are equal to 0. Divide the 2 and you get 4x squared minus x to the 4th equals 0, or the square root of. Take a look at that. The only way for a square root to actually equal 0 is if the radicand, the thing that's inside the square root, is equal to 0. And then I know how tempting it is right now to add x to the 4th to both sides, but that's not the best plan here. That's a good way to start losing roots, is when you start dividing by x. So the better thing to do here is to try and factor that left side. So let's factor the left side a little bit. Okay, that's probably as factored as you need. I know you're in calculus, so your algebra, you should be able to look at that and say, hey, I have a root here when x squared equals 0, which is the same thing as saying when x is equal to 0. And I also have roots when x squared is equal to 4, and that would happen at positive and negative 2. So your roots are 0, negative 2, and positive 2. That corresponds nicely with what we had initially estimated. if you take a look on the left side over here, this is x equals negative 2, this is x equals 0, and this is x equals 2. Now the first one over here at x equals negative 2, we can pretty much throw that away since we're only going to take a look, figure out the area on the right side and double it since our figure is symmetric. So the only ones that are interesting to us are x equals 0 and x equals 2. Those are going to be the lower limit and upper limit of our integral. So you get the area as the integral from 0 to 2 of 2 radical 4x squared minus x to the fourth, which is equal to 10 2/3. So your area here of the entire shaded region is 10 2/3. So there's a couple clever things we did here. Just to remind you, we had to find the intersection points of these graphs. Well, first of all, we had to analyze this as two graphs, the positive root and the negative root. Secondly, find those intersection points. And third, you needed to use you need to use some of the symmetric properties to make this a little bit easier on you. Which brings us to number 8. The national revenue of Urania is modeled by the function RT shown below, where T is years since January 1st, 2010, and RT is in millions of Uranian dollars, which I guess are called MUDs. Okay, Uranian's domestic expenditures are modeled by ET, also in MUDs, and I think, millions of, that's what MUD stands for, doesn't it? Millions of Uranian dollars. Okay, all right. The annual budget has a surplus if the revenue exceeds the expenditures, and if the expenditures exceed the revenue, then the budget runs what we call a deficit. The cumulative surplus deficit function in total surplus or deficit that Urania incurs at time t since January 1st, 2010. So first, describe that surplus deficit, or the surplus / deficit function. Well, that's just going to be r of t minus e of t, and then we're going to integrate that from year 0, which happens to be 2010, to year t, which is whatever year we're trying to figure out that function, revenue minus expenditure. So that function is the integral from 0 to t of rx minus ex dx. I want you to notice that since t is the upper limit of the integral, we can't very well have t also be the variable of integration. It doesn't really work that way. So we've just replaced it with x since, it is a dummy variable once we get down to the integral level. Letter B, find the value of expenditures of the function at January 1st, 2020, which is 10 years after 2010. So really I'm going to be evaluating d of 10, which will be the integral from 0 to 10 as well. Let's take a look at the work for that. There's definitely not enough room to put it right there, so we're going to slide over to the other side of the page. So my approach here is to figure out the r function first, or integrate r from 0 to 10, and then integrate e from 0 to 10 as well. So that integral of r from 0 to 10, notice that over here, your function r is a piecewise function, and there is a break of the piecewise function at t equals 5. The next break occurs at 25, so if I want to get the area from 0 to 10, which of course is the same thing as the integral, I'm going to have to find the area from 0 to 5 first, and then find the area from 5 to 10, and then add those two areas together. That's what you see here, the integral from 0 to 5 plus the integral from 5 to 10. Substitute those two functions as seen in that table which we just showed you. Neither of those integrals are particularly difficult, and you do get 62.5. I'm not going to show you all the integration here. You should be pretty familiar with that as well. So that takes care of it. The integral from 0 to 10 of r is 62.5. So what about the e integral? Just like the r integral, we're going to have to add a couple of different ones together to get the integral from 0 to 10. Notice that e has a break at t equals 2, and then another break at t equals 10. Well, we don't have to worry about going past 10 because that's going to be our right limit of our integral. But we do have to split our integral at t equals 2, just like we did for r at t equals 5. So the integral of e from 0 to 10 is the integral of e from 0 to 2 plus the integral of e from 2 to 10. Substitute in the equations from the piecewise function over there. And after you integrate, you should get 168. Again, just like the r function, I don't think we need to go into the details here on how to integrate this. This is a pretty simple integral, for most people, especially, if you're getting down to the AP test, you should be able to do these pretty easily. All right, what about that d function? Well, d is the integral from 0 to 10 of r minus e, and we know the integral of those two functions separately already. So you get d10 is going to be equal to 62.5 minus 168, which gives us a negative 105.5. That gets interpreted, since it's a negative number, as a deficit of 105.5 million Uranian dollars, or muds. A deficit, again, of 105.5 muds. And finally, for letter C, after 2010, where will the cumulative function be equal to 0? So basically, you want to know when is the integral of r equal to the integral of e. And for this one, notice that past 10, e is this function 1/2 t plus 22. And r is this function 2t minus 5 from 5 to 25. And then after 25, r is t plus 20. So if the integral of r is equal to the integral of e somewhere from 10 to 25, then we only have to deal with one integral. But if that one integral doesn't work, then we're going to basically have to take a look at two integrals. Let's look at the best case scenario right now, the easiest case scenario. So we start off with the function. We have the negative 105.5, which would be the deficit at t equals 10. And the integral from 10 to t of rt minus the integral from 10 to t of ex, when is that equal to 0? So at what point will we get that surplus deficit equal to 0? At this point, I would probably substitute the relevant functions. From here, integrate each one of those analytically. That's starting to look like a pretty gnarly function, of course. But what can we do? Remember that if I solve this and I get a t greater than 25, then I'm going to have to move on to that second integral from r. Fingers crossed we won't have to do that. Okay, let's do some substitution now. Okay, so here is our substitution. Let's clean that up a little bit. Noticing that there was a little bit of a problem here. That should have been a plus. Okay, so this doesn't look like something which we can solve with easy factoring skills. So we're going to have to move to a computer solver. So go ahead and grab your calculator and solve that. Let's see what we come up with. The two roots that I get are 3.693 and 32. Of course, we're looking for a value of t that's greater than 10 and less than 25, so neither of these actually work. So now the question becomes, well, what is the deficit when t equals 25? And I'm picking on 25 because you'll notice here at t equals 25, our r function changes. So our first next step is to figure out what is a deficit at t equals 25. Okay, so the deficit at t equals 25 is that initial deficit of negative 105.5 plus our deficits from 10 to 25, which is the the integral of rt minus the integral of et. Now we're continuing that same line of thought. We have our new deficit function is at negative 116 plus 75, which is the deficit at t equals 25, plus the integral from 10 to t of our r function minus the integral from 10 to t, and I see that's wrong. That should be from 25 to t. 25 to t of our e function. Now we're going to integrate again. Okay, so here's our new deficit equation. After an integral, we get this real mess of functions, and setting that equal to 0, of course. Combining like terms, we get 1/4 t squared minus 2t minus 223 equals 0. That looks like a pretty nice function as it is. And like we did before, this is actually these don't look like nice numbers anymore, so we're gonna use our calculator to solve for us. And we get t equals 34.133, or we get a deficit that disappears around 2044. Let's bring it back up over here, and there we go, our hard-fought results here. Our deficit disappearing at 2044. So that was a pretty intense set of problems, especially the end there. The piecewise function where we needed to integrate a couple different times, definitely more challenging than you would see in a lot of different applications. So that's it for us today, and I will see you next time when we do more calculus review.